All right, this next section, 310, related rates, is a application of derivatives, how we can, given some sort of equation or more likely a physical situation that naturally gives rise to some sort of equation from physics or geometry, how we can use that equation and the quantities therein to relate rates of change. If one quantity changes, and that quantity is related to some other quantity, then a rate of change of one quantity induces a rate of change in the other. And the rate at which one quantity changes isn't necessarily the same amount as their related quantities. So let's take a look at a physical example here. So, example one, consider a 10-meter ladder leaning against a wall, such as the side of a house. If the end of the ladder that rests against the ground is pulled away from the wall at a constant rate of 2 meters per second, at what rate is the tip of the ladder against the wall falling when the ladder is 4 meters above the ground? Okay, and there's a little follow up question here, which we'll talk about at the end. So let's say we have a wall of a house and then the ground, and then we've got a ladder leaning against it. Okay? Now, this ladder is 10 meters, so I can go ahead and label that with a 10. And then it might be tempting to label this distance as 4 because we are interested ultimately at the moment in time when the ladder is 4 meters above the ground. So this 4 is going to be used in the problem. But we're not going to label the side length with 4 because if we think of this process of this ladder slipping down the wall as this end of the ladder that rests against the ground is pulled away, if we think about this not statically but dynamically, then what's going to happen here is as time progresses, this ladder is going to kind of move like this as it falls to the ground. Something like that. So in actuality, this length here and this length here, they are not constants, right? They're going to be changing as this process unfolds. The reason why we're able to label this length as a 10 is because this ladder is 10 meters long. We're not assuming it's one of those ladders that, extends into itself. This is a ladder whose length is always 10 meters. So, rule of thumb here, when you're doing these problems, these related rate problems, in any given problem, there will likely be quantities that have a constant value the entire time, and there are going to be quantities where their values change over time, but you are specifically interested when that value is something. So in this case, this value, the length of this distance from the ground to the tip of the ladder, this distance is going to decrease as the ladder falls down. And we are interested in that moment of time when the ladder is exactly 4 meters above the ground. But because this length is not always 4 meters, it is going to vary. We're not going to be able to label this with a 4. So let's go ahead and label these two with just variables. So x and y. Okay. So what else do we know? We know that the ladder, this end along the ground, is going to be pulled away at a rate of 2 meters per second. So what this is saying effectively is that this distance here is increasing by 2 meters every second. So what we can do here is we can go ahead and say that we know that dx dt, the rate of change of x with respect to t, has to be 2 meters a second. And now what we're interested in this problem is our goal here. I'll just say that our goal for us is to figure out what dy dt is. So our goal is dy dt when y is 4. So we want to know how quickly is this distance changing? In other words, how fast or how quickly is the tip of the ladder falling. So those two things seem a little bit different. They're phrased differently, but they ultimately are the same thing. The rate at which this distance is changing is exactly the same as the speed at which this ladder tip is falling. They are one and the same. So ultimately, this is our goal. All right. Now that we have that sort of broken down and figured out, what we want to do now is go ahead and do the next step. So the first step of any problem is to draw some sort of representative diagram. And then you want to label anything that you know. So we fill in relevant information and identify what we need to solve for. So step 1 is sort of parsing all the information, figuring it out. So step 2 now, I would say, is to develop some sort of relationship between the quantities. So related rates means every problem you'll be given a rate and you need to figure out some other rate. These rates are related. If this moves, then this moves. So what you have to do now is figure out some way to relate x and y. Is there a way, some sort of equation that we can come up with to get x and y in the same equation? Well, most of these problems do boil down to geometry. This is a right angle, so this is a right triangle. And because this is a right triangle, we can use Pythagorean theorem. So a big, very common type of problem in related rates are problems that essentially boil down to a triangle, to the geometry of a triangle. It could be something like a car going through an intersection, two cars going at an intersection. You want to know how fast is the distance between the one car and the other car changing as the two cars travel. Well, that's a right triangle. So here, once we have our relationship, we want to go ahead and differentiate. So we'll differentiate with respect to time. And simplify. So this will be 2x dx dt plus 2y dy dt equals, well, this is a constant, so 0. Once we have that, we can simplify it a little bit by dividing everything by 2. So if we divide each piece by 2, we should have something like this. We'll have x dx dt plus y dy dt equals 0. Now, since we are ultimately interested in dy dt, we could also just immediately solve for dy dt. So let's do that. So dy dt is equal to negative x over y dx dt. All right. With that figured out, we now have the next step, which would be to plug in all of our information. So we know what dx dt is. That was given to us. This is going to become a 2. We do know that y is 4, but that does leave us with x. So even if we plug in all of our information, we still have this extra x that we need to figure out what to do with. Well, here's where you still have to think about this scenario here. When y is, so there, you can think of there being a moment in time where this distance y is exactly 4. This ladder is still 10, but now we have this. We need to figure out what is this x equal to when y is 4. Well, it's the same thing. It's still this Pythagorean theorem. This time we're just going to solve for x when y is equal to 4. So, in this case, x is the square root of 100 minus 4 squared, which is 16. So x is going to be the square root of 84, which should end up being the see if we do this all correctly. We should get x is equal to 2 square roots of 21. So with that in hand, now we are prepared to evaluate dy dt when y is 4. And this is negative the x value that we just found over the y value 4 times dx dt, which is 2, and the units then will be meters per second. If you simplify all of this, we'll get negative square root of 21 meters per second. And this makes sense. If this distance x is getting bigger, that means this distance here has to be getting smaller. So if this is a positive rate for growth or increasing, then this should be a negative rate for decreasing. All right, the follow-up question here is, let's see, follow-up question. As the tip of the ladder approaches the ground, so as y goes to 0, what happens to the velocity of the tip? What happens to the velocity? So in other words, if we rephrase this, essentially it's asking, as y goes to 0, what does dy dt approach? So this is definitely a limit. So let's take the limit as y goes to 0 from above, from the right. Okay. The ladder's not going to come up from underneath the ground, right? It's gonna drop from positive numbers to 0. So this will be a right-hand limit. The limit is y goes to 0 from the right of dy dt. Well, if we go ahead and replace this in, dy dt, before we plugged in all of our numbers here, dy dt was this. So this was negative the x value, and the x value is just the square root of 100 minus y squared, all over y. Times our dx dt. But this, right here, is going to be some constant number. So we don't have to worry about that. Effectively, what's going to happen here, if we think about this, in the numerator, so we're going to treat this as a constant. There's no y's in this derivative here. So this is just some constant. But here, the numerator is going to go to 10, right? The numerator is going to go to 10, but the denominator here is going to go to 0. So if we think about the graph of 1 over y, if this is the y-axis, then it would look something like this. Since we're doing a right-hand limit, we only care about this half. So this would be infinity. So the limit, so what does the speed approach as y goes to 0? It approaches infinite speed. What does this value seem feasible? No, we've all dropped things and we've never witnessed an infinite speed. So what's wrong here? What's wrong here is that this mathematical model that we chose to use here, it works when this when the ladder tip is sufficiently far from the wall. But if you actually reproduce this experiment in real life, what ends up happening here is the ladder's tip clings to the wall, but there's a certain point where there's enough there's a lack of friction at a certain point. There's some critical point on the wall. There's some critical angle where it's sufficiently small where it actually leaves the wall. So if you trace the ladder's the tip of the ladder, it would go down the wall like this, and then it would kind of slide out like that before hitting the ground. So it actually lets go of the wall. Our mathematical model assumes that it always makes contact with the wall, but physically that is not what happens if you do an experiment. So what's the takeaway here? The takeaway is whenever you apply mathematics to a real world problem, there's certain assumptions that you have to make in order to write down that model. Those assumptions may or may not be physically true. And whatever conclusions we draw from our mathematical model, they're going to be a result of those assumptions. So if any of those assumptions is not always true, then our mathematical model only has a narrow, not super narrow, but it has a specific range of applicability. It might not apply in all contexts. So when you apply math to the real world, you have to make assumptions, and based on that, your model may be more or less accurate.